Hi class, let's do some more linear algebra. For the last few lessons, we've been talking about the determinant. Right now, our goal is to, in part, gain an intuition about the determinant. We've been collecting a lot of different results. Sure, we can prove them, but how do we make them make sense? Well, one of the ways is that we're going to do it by figuring out a geometric interpretation of the determinant. In order to do this, we actually need to go on a little bit of a detour. It's not going to look related, but it certainly is related. We're going to take a detour back to vector spaces, and particularly the spans of vectors. Let's go. Given a vector space, V over R. So this is a real vector space. Remember, we don't actually need the reals to form a vector space over. We can form a vector space over the complexes or any other field. But for now, let's stick to real vector spaces. So say V is a real vector space, and we've got vectors V1 through Vn in our vector space. From this, we can create a new vector space. Definition. Say S is a non-empty subset of our vector space V. As in, S is just a collection of vectors. We say S is a subspace of V if 1, S is closed under scalar multiplication as defined on the ambient vector space V, and 2, S is closed under plus, however plus was defined in the ambient vector space V. In notation, number 1, S is closed under scalar multiplication, just means that for every x in S and alpha in the reals, alpha times x is also in S. And number 2, S is closed under plus, just means that for all vectors x and y in S, x plus y is in S. Before we talk about some examples, there's something that I want to point out that follows from this definition. Real quick, notice. Say we take a vector that happens to be in S. This also means that -1 times x is in S. How do we know this? Well, -1 is in the reals, and by 1, scalar multiples of elements of S are still in S because it's closed under scalar multiplication. We happen to know from the work that we've done before that -1 times x is the additive inverse of x. So because of that, -x is in S. Following from that discovery, we know that x plus -x is going to be in S, and this is the 0 vector from V. How do we know that? Because of 2. S is closed under addition. All of this is to say that the 0 vector is in any subspace of a vector space. Let's do some examples of subspaces. Example. Kind of building off that thing that we just noticed, 0 itself is a subspace. It's called the 0 subspace, unsurprisingly. It's also referred to as the trivial subspace. And you can go through and check that this actually follows or, fulfills the definition of a subspace. Here's another example. Say we've got V1 through Vn in here, in V, then the span of V1 through Vn is a subspace of V. And just to remind you what the span is, this is everything that can be expressed, every vector that can be expressed as a linear combination of the VI's. Example, V itself is considered to be a subspace of V. All right. Some of these things are more interesting than others, so this kind of motivates the definition of a proper subspace. A subspace of S of V is called a proper subspace if, sure, it contains 0, and yes, it must be contained in V, but it is bigger than 0 and in some sense smaller than V. Let's do an example. All right. Say we've got the XYZ space. We've got Euclidean space of dimension 3. Say we're looking at the plane spanned by these two vectors. So we've got this little vector here given by 1, 0, 0. And this vector here given by 0, 2, 0. The span of 1, 0, 0 and 0, 2, 0, it is actually the xy plane. And this is a proper subspace. Of R3. Claim. Claim 22. Every subspace of a vector space is itself a vector space. Here's the idea. It's closed under scalar multiplication and addition by definition. Everything else needed to be a vector space is inherited from the ambient space. Exercise. Establish this claim. All right. We've now defined subspaces and proper subspaces, and we have an example. But the reason that we like subspaces is because of claim 22. We are inherently interested in vector spaces for a lot of reasons that we've talked about and will continue to talk about. So when we're searching for examples of vector spaces, we can now realize that subspaces form examples of vector spaces. So now let's go through some examples. Example, Cn AB is the set of all real valued continuous functions f going from the interval a to b to r. It's real valued. But it's all real valued continuous functions that have nth derivatives on AB. This is an example of a subspace of CAB, which is all real valued continuous functions on the interval AB. Exercise. Answer: is CNAB a proper subspace of CAB? If yes, find a function that's in CAB that's not in CNAB. Let's do some more examples. Example. Well, for these next three examples, A, as usual, is going to be an n by n matrix with real entries. Call A. This is the column space of A. This is the span of the column vectors of the matrix A. Said otherwise, these are all the vectors B such that B is equal to AX for some X in Rn. Okay. This might be a little bit hard to parse, like why are these equivalent, especially this last statement. So let's just walk through this a little bit. The vector X is x1 through xn. A is a matrix, a11 through a1n, an1 through ann. Here's the first column vector, and here's the last column vector, etc., etc. How does matrix multiplication work? Well, B is going to be AX from our definition of the column space. But what does that mean? Well, x1 times the first column plus x2 times the second column, etc., all the way to xn. And remember, our xi are real numbers. So this just says that B is a linear combination of the columns of A, the column space of A. There's also, as you would expect, the row space of A, the row space of the matrix A. This is defined to be the span of the row vectors of A. We've talked about this a little bit before. There's also, note in notation, n of A. This is the null space of A. This is defined to be vectors x such that AX is equal to the 0 vector. Here's an exercise for you. Exercise. If A is an n by n matrix, show that n of A is a subspace of Rn. Let's walk through an example that's going to help us connect a lot of these concepts together. Example. Here's A. It's a 3 by 3 matrix, 2, 4, 1, 1, 3, 1, 3, 7, 2. So of course, here we've got A1, A2, and A3. Here's something that I don't expect you to know how to figure out right now, but something that is easy to check. A3, the third column of A, is equal to A1 plus A2. This means that A1, well, minus the vector A1, minus the vector A2, plus the vector A3 is going to be equal to the 0 vector. This means that negative 1, 1 is a solution to AX is equal to 0. The negative 1, and 1 are the coefficients of the column vectors of A. But since this is a solution to AX is equal to 0, this means that negative 1, 1 is in the null space of A. This happened because A2 was in the span of A1, A3, my apologies, was in the span of A1 and A2, using our new notation. The column space of A is a plane. It's not three-dimensional space, even though there are three vectors. It's a plane, and it's two-dimensional instead of R3. In order to link this to the geometry, I'm just going to actually draw this for you, or pull in a drawing of this for you. Here is a picture of these three vectors. Let me just orient you briefly. We've got the x, y, and z directions. Here is the x direction. Here is the z direction, as you can see on the side. And here is, of course, the y direction. I've sketched the three vectors, so remember A1 is 2, 4, 1. A2 is 1, 3, 1. And A3 is 3, 7, 2. This vector here is A1. Over here we've got A2, and in the dashed line we've got A3. And as we can see here, A1 and A2 define some kind of plane, and because A1 and A2 create a span and A3 lies in that span, that just means that A3 is in the plane defined by A1 and A2. And suddenly we have a geometric interpretation of this column space of a matrix. And we can see when it has a certain number of dimensions, 2 versus 3. Here's another exercise for you. Prove that this matrix A, 2, 4, 1, 1, 3, 1, 3, 7, 2, is not row equivalent to I. Let's end here. I expect you to have many questions. What does the spanning have to do with the ideas that we've been encountering before? In particular, if we take the span of the columns, is there a relationship between the size of the column space, however we define this, and the ideas we've been exploring like, I don't know, the determinant? The answer is yes. And hopefully over the next 2 lessons, we'll be able to figure out what exactly this relationship is. Think on this. Talk to you next time.